Hello, my name is Griffin Williams, and this is for Dr. Cormier's third and final video project. And today I will be discussing diffraction. Now, bear with me because my cameraman is half chair for half the presentation and half me for the rest of the presentation. You'll still be able to understand everything because it's my voice and you can easily understand my voice. Now, the definition of diffraction is diffraction refers to various phenomena which occur when a wave encounters an obstacle. In classical physics, the diffraction phenomenon is described as apparent bending of waves around small obstacles and the spreading out of waves past small openings. Now, diffraction was first coined by Francesco Maria Grimaldi in Italy in 1665, and he was the first to record the phenomenon. Diffraction occurs with all waves, including sound waves, water waves, and electromagnetic waves, such as visible light, X-rays, and even radio waves. Further, as has been discovered, physical objects have wave-like properties at the atomic level. So therefore, diffraction does occur and can be studied at the quantum level. Now, today's problem will be using diffraction gratings. Excuse me. And a diffraction grating is an optical component with a regular pattern, or an array of a large number of parallel slits, all with the same distance and spaced at equal distances between centers. The form of the light diffracted by, or wave diffracted by a grating depends on the structure of the elements and the number of elements present, but all have intensity maxima at angles theta, which are given to the grating equation. Now, from now I'm going to take the camera and discuss it from behind because I have to show you on the board. Now, the equation for diffraction grating is d sine theta is equal to m lambda, which is written right there. Now, the theta is the angle which the light is incident to the slits. The d is the distance between the slits on the grating, which is equal. M is the integer number that states which order of spectrum of the wave we are dealing with. And lambda is the frequency of the wave. Now, the problem I will be dealing with is number 28 from the book. 3 discrete spectral lines occur at angles 10.1 degrees, 13.7 degrees, and 14.8 degrees in the first order spectrum, so therefore m is equal to 1, of a grating spectrometer, which is a diffraction grating. The first part is A, if the grating has 3,600 slits per centimeter, what are the wavelengths of the light for each different angle? And for B, at what angles are these lines found in the second order spectrum, where m will be equal to 2. Now, know, as we discovered, that the equation is d sine theta is equal to m lambda. For the first part of the equation, A, we can change it around, just algebra, to d sine theta over m is equal to lambda. And to find d, we know that per centimeter, which is 1 times 10 to the negative 2 meters, it's easy math, divided by 3,600, which is the amount of slits per centimeter, is equal to 2.732 times 10 to the negative 6 meter, which is equal to 2,732 nanometers. Now, we choose nanometers because nanometers are the typical use for lambda, the wavelength. So therefore, we will move on to A. So note, it's the first order, so m is equal to 1. So that equation, d sine theta over m is equal to lambda, can become d sine theta is equal to lambda, because m, when you divide by 1, it doesn't matter. So for the first part, for the first angle, 10.1 degrees, we plug in the numbers into the equation. So as stated, d is equal to 2,732 nanometers, and sine theta, which is equal to 10.1 degrees. We find that that is equal to 479.1 nanometers, which is for 10.1 degrees is the number for lambda. Now for 13.7 degrees, we do the same exact thing, and we get 2,732 nanometers. times sine 13.7 degrees, which is equal to 647 nanometers is equal to lambda. For the last one, 14.8 degrees, we plug that in also, and we get 2,732 sine 14.8, which is equal to 697.9 nanometers for lambda. Now, as stated, for B, we are trying to find the angles that these lines are found in the second order spectrum. So we have to actually use the lambdas for every degree to find a new angle for the second order. Therefore, m is equal to 2, and when you're finding an angle, you use the arc sine. And when played around with algebra, we know that the equation we're going to be using is arc sine, or the inverse sine, of 2 theta over d, which d is constant, and we're finding for different lambdas. So for the first one, which was originally at 10.1 degrees in the first order, we're finding it for the second order. Now, the angle, of course, is going to change because only the wavelength is the wavelength, or lambda, is constant during the different orders of spectrums. So therefore, for the first one, as we found, the wavelength is 479.1 nanometers. So we find arc sine of 2 times 479.1 nanometers divided by 2,732 nanometers, which is just d, and that comes to 20.53 degrees for theta. Now for the second one, where our lambda is equal to 647 nanometers, we find arc sine of 2 times 647 divided by 2,732 nanometers, which is equal to 28.27 degrees for theta. Finally, we see for the same thing for 697.9 nanometers for lambda, we take the arc sine of 2 times 697.9 nanometers divided by 2,732 nanometers, which gives us 30.72 degrees for theta. Now that is my project for our final project, and I hope you enjoyed it, Dr. Cormier, and I will see you in class for our test. Cheers.